So just to kind of intro today's contents a bit, we posted the link to the agenda over there in the chat window. Please feel free to jump in, sign in on the document. It's a community document. You can add to the notes. Alan will kind of oversee getting the core things in there. We are recording again today. We will be able to post this up later on to the YouTube channel. So like we did last time, if there are any questions anybody would like to ask that you don't want to ask on your own, you're welcome to send a direct message to Alan or myself, and we're happy to ask it on your behalf anonymously out to the meeting. But today's topic, we have Michael Jennings from LANL, who will be here to present on CharlieCloud. And if there are no additional questions, we will turn the time over to Michael.
All right, thanks, Brian. Can everybody hear me okay?
Yep.
Yep.
All right, good deal. So my name is Michael Jennings. I'm the platforms team lead in the HPC systems group at Los Alamos National Lab. I lead the team responsible for the day-to-day system administration for all of our supercomputing clusters. Let's see here. There we go. So if you're not familiar with LANL, we were created back in 1943 as the super secret site of the Manhattan Project. We are responsible, along with Lawrence Livermore and Sandia Labs, for the assuring the safety, security, and effectiveness of the U.S. nuclear stockpile. That's not all we do. We do lots of research in energy, environment, medicine, nanotechnology, all sorts of stuff. But since the test ban back in 1992, when they decided it was probably not such a good thing to blow up nuclear devices on a regular basis, we have relied entirely on supercomputing and simulations to continue doing the maintenance of the stockpile. So as you might imagine, supercomputing is extremely critical to what we do and how we do it. We have been doing high performance computing here at LANL for a very long time, even before high performance computing was a thing. We had the very first vector computer. We had #1 on the original top 500 list, and more recently our Roadrunner machine was the first to break the petaflop barrier. Today we have a machine called Trinity, which is a Cray XC40 that offers something called a burst buffer, which was also created here at Los Alamos. And we serve over 2,000 unique users across both our open computing and classified computing systems. So I know this group is based primarily on research computing. So just so you're aware, before I came to LANL, I spent almost 10 years at Lawrence Berkeley National Lab and participated with the research computing team at UC Berkeley. So I do have a background in campus research computing as well. So in HPC, especially in the past few years, we have started encountering some challenges that we had not seen before in our line of work. It used to be that HPC and research computing were the cutting edge of our industry. Everyone relied on the large-scale systems at the national labs to kind of set the direction for the industry and do all of the bleeding-edge research and technology. That's no longer the case. The Googles and Facebooks and Amazons of the world have blown past us and created something called hyperscale, which is great for innovation and driving technology. Unfortunately, it caters to a very different problem space than traditional high-performance computing. We still have the problem, though, that most colleges don't teach science and HPC. They are more geared toward getting people ready to use the cloud. So instead of students coming out of college ready to roll on Red Hat and SUSE, a lot of them are using Debian and Ubuntu in particular, largely because they can apt-get install just about anything that has ever been created on the planet Earth. Unfortunately for us, those operating systems aren't really tailored toward the supercomputing environments that we're used to. And so we have this fundamental conflict that more and more of our users today are wanting to run applications on operating systems that don't really fit with what we've been doing for a long time. We have always built systems that were focused around running our scalable parallel jobs, mostly MPI jobs. And we can build MPI systems very, very well. But now we need to expand our horizons a bit to cater to the newer users, the younger users who are relying more and more heavily on these other operating systems, as well as, particularly in the world of Python, it's not uncommon for somebody to write a Python script that uses a few dozen modules, even upwards of 100 modules in one single utility. And if you've ever had experience with a large-scale cluster trying to launch a Python job where one process per core on every one of 20,000 nodes all try to hit the file system at the same time to load 150 Python modules, well, you know how that story ends. So that's one problem we need to solve. We also need to address the combinatorics problem of HPC software management. I'm sure most of you are familiar with that issue. Each compiler that you need, each MPI library that you need, all the different software packages that you have to build for your users, a lot of times you have to build each and every combination of all of these different things. And the problem becomes untenable very quickly. And we just don't have the personnel and the time to be able to manage the complexity of this entire problem space with, particularly in the research computing and academia worlds, what are typically very small teams. It's also fairly common for particular users to have specific version requirements of libraries that are often supplied with the distribution that we run. The little graphic there mentions glibc specifically. And as scary as it might be, I have had customers in the past come to me and ask me to install literally the master Git branch of the current working glibc onto the system for them. I've also had customers ask for root access so they could install their software without having to wait on me. Obviously, those are not scalable in terms of solutions to their problems, but they are real legitimate issues that we have to try to resolve. So how do we do that? Well, the ideal scenario is to allow our users, our customers, to couple the application or applications that they want to run on the HPC resource with the environment that they want it to run in. There are a few different terms for this. We use user-defined software stacks. Other sites use user-defined images or bring your own environment. Mobility of compute is another common term for the same thing, but it all boils down to allowing the HPC users, when they submit a job, to not only specify the application that they want to run, but specify the operating system or operating environment that the application needs in order to run successfully. Now, back in the olden days, the way you did this was to build static binaries. A static binary, of course, is one that has all of the libraries that it needs tacked onto it. Not all applications are buildable as static binaries, and even when they are, if you've tried to build a static binary recently, you've probably noticed messages from the linker that warns you about needing the actual libraries at runtime. It's not impossible, but pretty close to impossible to build many applications today statically if they're traditional C or C++ or Fortran applications. Go is very good at building static binaries, but for all of the other languages and scripting languages like Perl and Python in particular, it's rarely feasible, let alone practical, to build statically. So in a perfect world, our users would come with an application perfectly suited to the exact operating environment that we have on our systems. But as you all know already, different centers have different operating systems, different versions of operating systems, and there's just no way for our scientists to build a single application that will just run everywhere. So we need a better way. Option number one is telling our users, go compile it yourself on our system. That sounds great for us because it's no additional work. Unfortunately, for our users, that puts all of the burden either on them or on our user services or consulting personnel to be able to build all of that software. It's great that there's no performance penalty. It's great that the software knows exactly what hardware it's going to be running on and so forth. But building for a specific cluster is a one-time thing. And the moment you do a hardware upgrade or they have to take their application to a different cluster, you have to start all over again. It's also very rare to have those types of builds be done prescriptively or in any sort of repeatable fashion. So when the next version of a library or an application comes out, again, you're starting over from scratch. Computers are great at doing the same thing over and over and over again in exactly the same way. People aren't really good at that. So this is probably not the correct solution to our problem. Option number two is probably the one that is most common in HPC and research computing centers today, what's called an environment manager. So this is something like environment modules or LMOD and so forth. An environment manager allows the user to pick and choose among the options that the system provides in terms of compilers, parallel libraries, debuggers, visualization tools, and so forth. Unless you couple it with some additional software, though, you still have that same combinatorics problem that I mentioned earlier. And somebody, whether it's the customer or their postdoc or a project team or whomever it happens to be, somebody is still on the hook to build and manage all of these different pieces of software. Now, if that's the route that your particular site has chosen, there are today some really good tools for helping make that easier to manage. The first one that came out that I remember was Easy Build. It helps to standardize the build process for a lot of software packages that are common in HPC and make it easier to build those. A more recent addition is something called SPAC. SPAC allows you to define how to build different pieces of software in a way that you can share with the rest of the community and prescriptively build and manage the entire dependency space of a complex set of packages. If you're familiar with the exascale computing project of DOE, its mandate is to solve a lot of the challenges of getting to computing at exascale. And SPAC is the chosen software build and package manager for the exascale computing project. So it is under heavy active development. There's a lot of new features coming in, including SPAC stacks and binary builds, pre-built binaries and such that you can download from a central repository and so forth. So it's definitely a solution that's worth looking into. There's also Anaconda, which you've probably heard of. It's a pre-built distribution for Python and associated modules. There's something called NixOS, which allows you to prescriptively define the configuration for an entire operating system or set of utilities, and you can install it in your home directory. So that's another option that sometimes customers have chosen. But even so, there's still a lot of time and effort and engineering involved in setting up these massive trees and graphs of dependency chains for all the libraries and applications. So there's got to be a better way to manage all of that. Option number 3 is virtualization. If you've been in high performance computing or research computing for any appreciable length of time at all, you have probably had at least a few customers come and ask you to deploy virtualization in some form or fashion. This is typically the cloud solution to the problem. And while virtualization technologies have come a long way in the recent past, there's still a lot of downsides to using virtualization, as you can see from the slide there. The big one is always performance. Anytime you are emulating something in software rather than allowing direct hardware access, it's always going to be slower. Sometimes it's a little bit slower, sometimes it's a lot slower, but it always is slower. If you employ something called para-virtualization, which the KVM modules on the Linux kernel provide, those can enhance performance, but they do it at the expense of isolation. So it's a trade-off. You can make things go faster, but anytime you're running on the actual bare metal hardware, there are risks associated with that. And anybody who's tracking the bugs in QEMU, KVM, and Zen, and so forth, there are new bugs coming out for both of those on a fairly regular basis. So it's definitely not an ideal solution in terms of reliability or security. There's also a lot of complexity in setting up a cloud-like environment. You have to deal with the network and often overlapping networks, separate firewalls. You got to worry about keeping different virtual clusters separate from each other. And if your users are supplying their own VMs, there are obvious security implications to that, because you're basically adding a new host to your system. Historically, in HPC and research computing, we have relied on some sort of barrier between the outside world and the high-performance cluster for the security of the system. If somebody can get through that outer layer of security into the cluster, typically they can move around inside the cluster and do whatever they want once they get in there. We used to refer to it as a firm outer shell and a mushy center. And when you're allowing users to bring in arbitrary VMs inside that mushy center, there's definitely risk associated with that. So while I do think that eventually HPC and the cloud are going to merge, or at least find a significant amount of common ground, we are definitely not at the point yet where that makes a lot of sense, at least for the ultra scale, tightly coupled applications that we deal with day to day. Option number 4, containers. Containers are kind of the ideal balance between making it flexible enough and making it isolated and safe enough. I'll go into more detail on what that means exactly here in a little bit. Containers also offer an industry standard prescriptive way of building and managing containers, which makes it easy to allow someone else, should they so desire, to create the same or very similar container to what you created, so they can reproduce the environment that they need to run in. Since containers don't involve any sort of virtualization of hardware, you get bare metal performance, or pretty close to it. And since a lot of projects are already supplying their own container images or instructions to build containers, this greatly reduces the end user burden, as well as the user support, user services burden of building applications, because containers allow the application to bring its environment along with it, so that all of the dependencies, all of the supporting libraries, and everything, it's all bundled into this one container. There are some downsides. You have to have a fairly recent distribution, recent being a relative term. For those who've been in HPC for a while, enterprise distributions like Red Hat Enterprise and SUSE Enterprise tend to lag behind their counterparts on the desktop like Fedora and Ubuntu. So it's not always trivial to get a recent operating system with a recent kernel that has all the right tooling that you need. Specifically, you need SUSE Linux Enterprise 12 SP2 or later, or Red Hat Enterprise 7.4 or later. The current version, 7.6, supports containers out of the box, as does the current SLES 15. Any recent Ubuntu or any recent Linux LTS kernel will also support the right stuff. If you don't have a recent enough distribution, you may still be able to run containers. You just need a privileged runtime to do it. And I'll go into details in a little bit. Defining the term new in computing in general and high performance computing specifically is always a challenge. Unix has been around since the 70s, and so new could mean within the past year, or new could mean within the past decade. So when we say that containers are relatively new, we mean the latter. The container implementation in the kernel as it currently exists was feature complete back in 2013, and it's been roughly unchanged and considered secure since 2015. So fairly recent, but not exactly bleeding edge. And there's still a lot of people out in the HPC and research computing world who are getting up to speed on containers. I mentioned earlier that HPC used to be driving the technology curve. Well, now the hyperscale and cloud providers are doing a lot of that. And containers originally came out of that realm. So HPC now is kind of playing catch up to the hyperscale and cloud providers out there, which is a role switch for us. It's not something that we're really accustomed to. And there's been a lot of myth and misinformation and misunderstanding out there about containers. So hopefully we can clear some of that up. But containers do offer a great balance between performance and isolation and security. So that's what we chose as our approach to solving this problem. So what are containers? That's actually a really good question. Many different people or different projects use that term loosely or have different definitions or understandings of what that term means. So we'll take a moment and I will lay out what the definition that we use, understanding that other people or other projects might use the term slightly differently. So Linux containers use a feature of the kernel called namespaces. Generally speaking, in order to call it a container, you need to be using at least one namespace, possibly multiple, and you can combine namespaces with other kernel features that provide additional capabilities. Those additional features aren't technically required for it to be considered a container, but they often help in terms of security or isolation, logging, things like that. Containers also provide a false or distorted view of the underlying system and the resources that it makes available. Brian Cantrell of Joyent and formerly Sun Microsystems fame coined the term lying. Containers are lies that we tell our applications. So containers are a way of misrepresenting what is or is not available on the system. Containers also envelop and restrict unprivileged processes in order to prevent them from escaping out of the container. Now, if your container process is running as root, and that's root on the host system, then it can easily move between namespaces. So this is specifically about unprivileged processes running as non-root users without capabilities. Containers confine those processes so that they can't try to escape and get the real view of what's on the system. And then containers provide extra application security features like capability constraints, which the Linux kernel offers a feature called capabilities, which I'll get into in a little bit. Integrity assurance, meaning that the content that was originally in the container when it was built is the same as the content that we're running in today. And content validation via industry standard formats and workflows, at least for application containers. Not all containers are application containers, but the ones that we'll be talking about today and the ones that are used in HPC primarily are. But the key takeaway is containers are processes. At least one process, possibly multiple, each process and all of its child processes, all of its descendants. Containers allow us to take all of these processes and group them together and present the same lie, the same false system image to them. So namespaces are the kernel feature that facilitate that lying, that misrepresenting of the system. Current kernels support a total of 7 different types of namespace. And back in before 4.6, including the RHEL 7 kernel, there were only 6 types of namespace. 4.6 and beyond, there are 7. 6 of those types of namespace are what we call privileged. That means that a normal user cannot create those types of namespace. Specifically, there's a Linux kernel capability called CaRCC admin that is required to create these privileged namespaces. If you remember your Unix history and previous incarnations of Unix like Solaris and HPUX and IRIX, you always had the notion that root was God. Root could do anything and everything. Once you had UID 0, you had carte blanche. If you didn't have UID 0, you were restricted to whatever an unprivileged user could do. So it was very binary, very black and white, which meant that a lot of things on the system that needed to do stuff that a normal user shouldn't be able to do had to run setuid root in order to facilitate that. A good example is the ping command. Ping has to be able to open what's called a raw socket. And in order to make that work safely, that's restricted to root. So the ping command historically has always been setuid root. Well, the kernel, the Linux kernel, invented this concept of capabilities, which allow for the divvying up of certain types of privilege among these capabilities. So, for example, there's one called capnet raw, which allows for the opening of a raw socket. So today, for example, in Red Hat Enterprise 7, you'll notice that ping is no longer setuid root. That's because the file system allows it the capability to do what it needs to do without needing full root access. As with many systems that divvy things up, there's always an other or a miscellaneous category for stuff that doesn't fit in anywhere else. And in Linux kernel capabilities, that's what CaRCC admin is. Anything that they don't have a specific category for goes in CaRCC admin. So that's the capability that is required to create any of the privileged namespaces. The first one that was created is the mount namespace. The mount namespace provides the ability to mount and unmount file systems and change the view of the file systems and what's mounted and what's not for specific processes without affecting the rest of the system. So if I create a mount namespace, I can unmount a bunch of file systems, pivot root into a new root file system, and present a completely different operating system to that mount namespace as if it was the original Flash. PID namespace is for process IDs. Once you create a PID namespace, the process that starts that PID namespace is process ID 1, which traditionally has been reserved for init or systemd. And all of the responsibilities associated with that, like reaping child processes whose parent died, all of that stuff is true for PID namespaces as well. The UTS namespace doesn't do much. All it has is the host name and the domain name. That's not DNS domain name, that's NIS domain name. And if you are older than 30, you probably know what NIS is. If you're younger, you probably don't. It's not used much anymore. So that one is largely useless, but being able to set a custom host name is quite handy. So that's what UTS is generally used for. The network namespace gives you your own private set of network resources. That's interfaces, the entire networking stack, IP addresses, routing tables, IP tables rules, all of that stuff. You can have your very own set of all of that with a network namespace. When you create a network namespace, the only thing that goes in it is loopback. So if you actually want to talk on a real network, then you have more work to do apart from just creating a network namespace. IPC namespace allows you to have private IPC resources. This is like POSIX message queues, semaphores, System 5 IPC objects, and so forth. The most recent namespace that was added in the 4.6 kernel is the C group namespace. We'll talk about C groups in more detail in just a little bit, but the C group namespace allows you to have your own custom view of the C group hierarchy. Now, all of those namespaces, you have to have CaRCC in order to create those. There is one namespace that's unique that can be created by any user on the system. And what's important about that is that if you create a user namespace, you can also create any or all of the privileged namespaces at the same time or subsequently. So if you create a user namespace, you can then also create a mount namespace and a PID namespace and a UTS namespace and so forth. The user namespace allows you to have private UID and GID mappings. So if you're root, if you have CaRCC and you create a user namespace, then you can say, okay, I want these 10,000 UIDs on my host system to map to these 10,000 UIDs inside my namespace, and same with GIDs. If you're not privileged, then when you create a user namespace, you get exactly one mapping each, one UID, one GID. So you can say, I want my real UID on the host to map to whatever you want, and the same with GID. Most often, the mapping that's used is, of course, 0 for root. So within a user namespace, you can be UID 0, GID 0, so your root. And outside the namespace, you are whatever your real UID and GID happen to be. Additionally, when you create a user namespace, the process that initializes the user namespace gets all kernel capabilities, capsysadmin included, inside the namespace, but it has no capabilities outside the namespace. So inside a user namespace, you are fully capable, fully root. You can do anything you need to do until something touches the outside world. If inside of a user namespace where you're root, you try to access a file on, let's say, Lustre or GPFS, that access is done by your real UID and GID. And if you don't have, if your real UID and GID don't have access to a particular directory or a particular file, even though inside the namespace you're UID 0 and have all capabilities, you'll still get permission denied. There are 3 system calls that the kernel provides that are the interface for managing namespaces. The first one is called unshare. You can call unshare and tell the kernel one or more namespaces that you want to unshare from your parent. So you're creating new namespaces and putting the current process into them. Clone is the system call that is used to create new threads or new processes on Linux. And you can, when you fork off or when you clone off a new thread or new process, you can specify one or more namespaces, if you choose, that that process is going to exist in. And then setNS is the system call that allows a process, if it has appropriate access and privilege, that process can change its current namespace to another existing namespace. If all of this sounds really, really interesting to you and you want to learn more, there's a great series of articles on Linux Weekly News that I linked to there on the slide. I highly recommend it. That's how I got started. So if you want to read more, that's a great place to go. So I mentioned earlier that there are additional kernel features that can optionally be used with namespaces to facilitate containers. C groups or control groups are a relatively recent kernel feature that allows applications or processes to place resource limits or constraints on processes in a way that we never could before. For example, for many years, if a resource manager or scheduler wanted to put a limit on the amount of memory that a user job could consume, it had to sit there and check how much memory it was using over and over and over again to see if eventually it exceeded its limit. And then if it detected that the application had gotten too big, then it could take action. With C groups, you can actually tell the kernel to enforce a memory limit on the application. So then the kernel takes care of preventing it from using up too much memory. You can also limit how much CPU time a process or group of processes can use. And if that limit gets reached, the kernel itself will just stop scheduling that task until the limit it goes back underneath the limit. You can limit network bandwidth, you can limit disk I/O and so forth. There's lots of different constraints you can apply to a process or a group of processes via C groups. Seccomp BPF. BPF stands for Berkeley Packet Filter. It's basically an in-memory language. You can write little miniature programs using preprocessor directives and bytecode, and they'll actually execute in memory. It's extremely fast and extremely efficient. It was originally created for the purpose of matching network packets. That's how the BSD firewall works, for example. Well, recently, people in the Linux world have discovered that it's great for other things as well. And they've implemented BPF-based techniques for doing everything from performance tuning to actually replacing the traditional firewall mechanisms with BPF-based mechanisms. SecComp BPF specifically allows you to determine exactly which system calls an application is or isn't allowed to use. And again, it's enforced at the kernel level. So if an application tries to open a socket and you have a SecComp BPF config that says the socket system call is disallowed, then the kernel will terminate that process immediately. This is a great way to secure applications by limiting what they're allowed to do, so that if, say, there's a buffer overflow that compromises a particular application, that application is limited in what it's allowed to do and how it's allowed to proceed from that point. PRCuddle, or privilege control, is a system call that Linux uses to manage process privilege. There's a lot of different flags and stuff that you can use with PRCuddle, but the one that's most important for containers is a flag called no new privs. Once this flag is set on a process, it can never be unset. And it tells the kernel that no additional privileges should ever be granted to this process or any of its children. So even if that process executes a setuid or setgid binary, for example, it won't work because no new privs has been set. If you have an older kernel like RHEL 6 that doesn't support the modern container stuff, you absolutely must have this flag in order to make containers safe. There are a lot of edge cases and corner cases that can occur, and it's essentially impossible to make containers safe without being able to set this flag. SE Linux, you've probably heard of. It's a way of defining precisely what things a particular application can or can't do. It's a mandatory access control or mandatory labeling system for files and processes. It's complicated, it's difficult to learn, but it's extremely powerful. And you can tell the file system when a particular binary runs, it should have this set of labels or this label. And files and directories on the file system also have their own labels, so you can restrict what a particular application is or is not allowed to access, even if it's root. If it doesn't have the right label, it gets disallowed. AppArmor is a similar system, but it uses profiles instead of labeling. It's a lot easier to learn, but it's not as powerful, and you can't label things on the file system. AppArmor is generally the chosen route for Debian and Ubuntu. SE Linux is used on Red Hat Enterprise. So there are a lot of container runtimes and various software out there today. There are a few of what we call full-featured container systems, ones that do everything. The biggest and most common, of course, is Docker. But there are others, for example, there's LXC and LXD, which provide VM cloud-like vSphere, vMotion type of features. You can do live migration, you can do snapshotting, and so forth. In the world of application containers, Docker was kind of the one that facilitated containers exploding in popularity and really taking off. Docker made it really easy to build containers and share containers and move containers around between different systems. They also created Dockerfile, which is the de facto standard for how you prescriptively build containers, either from scratch or from a base operating system image. CoreOS came out with a competing project called Rocket, which resulted in the Open Containers Initiative, OCI, being created to standardize. Rocket used a shell-based system for building containers rather than the domain-specific language that Docker files use. And then more recently, Red Hat's Project Atomic, and now CRIO, came out with something called Builda. Builda is their container builder solution, and it actually supports both Docker files and building in a more shell-like syntax. For lightweight container systems, these are ones that generally only implement a portion of what's necessary for containers. Typically just the runtimes, the thing that actually runs the container itself. Runc is the one that's used by Docker. It's the OCI standard runtime for containers. There's a runtime called CCon, which is a container runtime that's OCI compliant and GPL'd, written entirely in C. There's a shell command you can actually use on most modern systems called unshare, which hides all of the complexity of how containers get created and how you do different namespaces and so forth. So you can actually write container implementations in straight bash. As with everything else, systemd has its own container implementation as well. You can actually boot a container using systemd nspawn, and it will launch the systemd inside the container as if it were booting a host. And there's a brand new project created by CSCS called Saris, which is an OCI compliant HPC focused runtime that's just been created recently. And of course, CharlieCloud. So I want to talk about container security for just a little bit. Before you run containers, the security of the container generally depends on the content being created correctly, transported correctly, and so forth, so that we know that the container that we're running has not been altered or changed in any sort of malicious way. Then at runtime, it's the container runtime and the kernel that are responsible for the security of the container. If the kernel's broken, then the container is broken as well. Generally, with lightweight solutions like CharlieCloud, a lot of the transport security stuff is left to other products, in this case, Docker. So you build your container with Docker, you upload it to Docker Hub or a registry server, whatever, and then CharlieCloud allows you or provides the tools that allow you to convert your Docker container into CharlieCloud directory tree and then launch that container on an HPC system. Whichever container solution you use, fundamentally, we're exposing privileged operations to unprivileged users. So we have to make a decision as to how we're going to manage that new privilege boundary, that security boundary. And the choice is, do we use a setuid application that we are now trusting with the security of our system, or as in CharlieCloud, we use user namespaces, unprivileged user namespaces, so the kernel is entirely managing that security boundary. And that's the thing that we already trust to maintain the privilege on our system. So with CharlieCloud and with user namespaces, you only trust the kernel and nothing else. With setuid container systems, you have to trust not only the kernel, but that particular application was written securely as well. So CharlieCloud is LANL's container runtime. It's available on GitHub under HPC/CharlieCloud. We just released 0.99 recently. We've got lots of great examples and documentation. We have a sample Vagrant file that will build you a VM that's capable of running Docker and CharlieCloud, so you can play around with it. There's new utilities to support high-speed networks and GPUs and all sorts of stuff, and we're actively working on getting a spec file that is anal retentive enough that Fedora will accept it into the upstream distribution. So hopefully that will happen soon. But CharlieCloud is completely unprivileged, so any user can install it, and as long as the kernel supports user namespaces, it'll just work. That includes current RHEL as well as current SUSE, and Debian and Ubuntu, of course.
Hey, Michael, if I can add quick.
Yep.
So we're close to the top of the hour. For anybody who is on a tight schedule, we will, as I noted in the chat, we will continue to keep this going as long as Michael has time, and then finish things out and post the recording later. For those who have to leave, thanks for being here. For everybody else, we'll keep going. So back to Mike.
All right, thanks, Brian. And the slides have been approved, so I will provide a link where they can be downloaded at the end for anybody who's interested. So why CharlieCloud? Why not use something else that already exists? Why not Docker, for example? Well, Docker and the Moby project, which is the starting point for Docker, they are not really a good fit for HPC. Now, there are various efforts going on to try and help Docker maybe improve its usability for HPC. There was a person until recently who was working at Docker Inc. trying to promote the HPC use case. He is no longer there, but we are still hopeful that at some point we can get to the point where Docker itself is usable in an HPC context. But as it stands today, the big challenge is around performance. The default way of managing container storage and container images is with something called overlay or overlay-fs. Overlay-fs is a way of combining different layers in a stack to gradually create your operating system image. When you build a container on Docker, each command that happens in your Docker file adds a new layer to your container image. And so if you yum install a bunch of stuff, then that becomes a layer. And then you compile your application and that becomes a layer. And then you copy in some files from your build tree and that becomes a layer, and so on and so forth. And then at runtime, the container implementation assembles these layers into an overlay FS, and any file access has to go all the way down through all of these layers to figure out if the file's there and what permissions are and so forth. So performance of overlay FS is not great at all. You also have the challenge of what happens when you remove a file. Because the lower layers are read-only, when you do a deletion with overlay FS, you actually can't delete any files that aren't in the current layer because all the lower layers are read-only. So what overlay actually does is a technique called whiting out, where it puts a file in place, an additional file that says, ignore this file in lower layers. So you don't actually remove anything that's not in the current layer, which means that if a previous build step put SSH private keys or my.cnf files with passwords or any sensitive information, if it was put into a lower layer, you can't delete it in an upper layer. It'll still actually be there, and you can go to the lower layers to get it. So there are definite security problems with that. There are also challenges around things like the RPM database, which you can have weird behavior to the point where they actually created a yum plugin for overlay FS specifically that just copies the entire RPM database up to the current layer for each and every layer. And with Docker, the Docker containers that you run aren't child processes of the Docker CLI that you're executing. They're child processes of the Docker daemon. So they're separate from the point at which you interact with Docker to launch the container. This presents problems for things like schedulers, because the container that you're running is not in the same process tree as the shell or the job script you launched it from. So there's an associativity problem there. Now, the first HPC-focused solution that came along was NERSC's Shifter. And Shifter has a great user experience. All the user has to do is run a command to pull the container down from Docker Hub or whatever registry server. And then they put one line in their job script that says, run my job in this container, and that's it, they're done. So it's great for the users. For the admins, though, there's a lot of setup and configuration overhead. You have to set up something called the image gateway, which is what does the actual pulling of the container. It converts the container into a squash FS for performance so that it can be distributed on a parallel file system as a single file rather than a directory tree, which keeps large jobs from pounding the metadata server of your parallel file system, which is great. And because it's based primarily on chroot, it needs to run privilege. So there's set UID associated with running Shifter. CharlieCloud went in exactly the opposite direction. Rather than trying to provide compatibility with older systems, CharlieCloud specifically went for user namespaces. User namespaces allow us to trust the kernel and only the kernel, and to run unprivileged so that there isn't a possibility of privilege escalation. We don't have to worry about vulnerabilities in the container image or vulnerabilities in CharlieCloud itself or any of those types of things. CharlieCloud also is an extremely lightweight and simple piece of software. When it was first released, it was under 1,000 lines of code. We've added some new features and new capabilities, so it's a little bit larger than 1,000 now, but still very, very small, especially related to other projects. Shifter is about 20,000 lines. Docker is over 160,000 lines, and so forth. So the code is clean and easily audited. And again, the security boundary for CharlieCloud is the kernel and nothing else. So you don't have to worry about vulnerabilities in CharlieCloud because there can't be any. Other things that we're keeping an eye on, there's a project called Podman, which came out of Red Hat along with Builda. Podman is literally a drop-in replacement for Docker. You can alias Docker equal Podman and all of your commands will continue to work. Podman currently supports unprivileged containers. Unfortunately, right now it only seems to work correctly on Fedora. So we're working on trying to make changes maybe that will make it a better solution for other platforms. And in particular, we are trying to put together a completely unprivileged workflow for containers. Currently, in order to use CharlieCloud, you have to use some other mechanism for building your container, whether it's Docker or yum install root or anything that can build a rootfs image you can use with CharlieCloud. But generally that takes privilege. With Builda, if we can fix some of the issues that it's having, we're hoping that we can create an entirely unprivileged workflow from start to finish. Very recently, somebody created a patch for Docker that allows it to run without root. We're definitely looking into that and the promises of what that might be able to do. And there's a project called Rootless Runc, which focuses specifically on the OCI runtime that allows it to run without root privileges as well. So this is a real quick walkthrough of what it's like to use CharlieCloud. Using chbuild, the first box is what you would do on your laptop or your desktop, someplace where you have root access. chbuild is a wrapper around the Docker build process, so you can use chbuild on your personal workstation to build the container inside of Docker, and then you run chdocker to tar to convert the Docker container into a tarball. Then you copy that tarball to your HPC resource. Then the second box there, that's what you do on the HPC system itself. You just run chtar to dir to convert the tarball into a container directory tree. How exactly you distribute that to all the nodes of your job is up to you. SquashFS, as I mentioned earlier, is a very popular solution. Or you can just put the entire tree on Lustre or GPFS. There are a bunch of different options that you can use. SBcast has been used, PDCP has been used, and so forth. But chtar to dir converts the tarball into a directory tree, and then chrun is the runtime. You just give it the path and any options that you might want to supply, and then the command that you want to run. So in this example, you can see that we created a Debian-based container, and it's running on a Red Hat-based system. So where do you find out more? Well, the original paper for CharlieCloud was published at Supercomputing 2017. I provided the link there for the tech report on our website. There was also an article in the Usenix magazine login that Reed wrote that was published in 2017 as well, and the link is there for that. The online documentation, we've put a lot of work recently into polishing the docs and making them more readable and easier to follow and so forth. So they are definitely worth a read through if you're interested about CharlieCloud or about containers in general. There's a lot of useful information. The source code, of course, is available on GitHub, and the examples are heavily documented. There's lots of examples, everything from basic MPI to TensorFlow. And there's documentation not only around some of the different applications and libraries like impitch and lamps and TensorFlow, but there's also documentation and examples in the source code itself around some of the interesting niggles about writing and using containers. We do have a mailing list that you can subscribe to, which is probably the best place for asking questions or getting assistance with anything. And of course, Reed, the primary author, and Tim and myself are always available via email if you have questions or feedback or anything like that. We're happy to have contributions or collaborations from admins or fellow developers or even scientists and other users. Since this is an unprivileged application, scientists can install it themselves rather than having to wait for the sysadmins to install it. So anyone and everyone is welcome to participate. And with that, that's all I've got. My email addresses and various social media identities are there if you're keen on getting in touch, and I'm happy to answer any questions.
So I'm trying to make sure if I've not muted somebody who wants to. If you're talking and asking questions, I did do a mute. Looks like Wayne Bradford might have a question. I'm not hearing you, Wayne.
Okay, we've got a question on chat from Martin. He asks, what options do we have, if any, to build a container as a user, not as root? So today, that's a bit of a challenge. Typically, what people have been doing is using Docker on like their desktop machine or their laptop or on a VM where they can get root and then build the container there. You can also use yum with the -- install root option to install into a directory tree. If you have a recent version of Fedora, you can install the Builda and Podman utilities and all of their dependencies on Fedora. And on recent Fedoras, you can run Builda as an unprivileged user and build containers from scratch unprivileged, and it will work. Unfortunately, some of the stuff that's part of the Builda code for building unprivileged that works on Fedora doesn't work on RHEL 7 even. So, and as I mentioned earlier, that's one of the things that we're trying to work through, see if we can patch those problems and if they might be open to if the upstream developers might be open to accepting our changes. So hopefully within the not too distant future, I will have a better answer. But for today, I'm afraid there's not a great answer. But ultimately, with CharlieCloud in particular, any mechanism that you can use to create what looks like a slash file system image, whether it's yum or apt, or even just tarring up the root directory of an existing VM or an existing server. Any of those things will work. Question from David Chin, what's a current distro that can run CharlieCloud? RHEL 7 and RHEL 8 do not seem to provide a new enough kernel. Actually, all versions of RHEL 7 from 7.4 on support user namespaces, and you can run CharlieCloud on them. And as of 7.6, it's fully supported out of the box. Before that, it was a technology preview, so you had to have a particular option on your kernel boot line to turn user namespaces on. With 7.6, there is a file in proc that you have to tell it the maximum number of user namespaces that are allowed on your system. The default is 0, so it's disabled, but you can increase that number to a billion or whatever, however many you want. And so you can do that at runtime, and that will allow CharlieCloud to work. If you look at the CharlieCloud documentation or the Vagrant file, it shows you exactly what file and proc that you need to up that limit. RHEL 8 will have a new enough kernel to fully support CharlieCloud. I have not played with it, so I'm not sure. I think the same is true for RHEL 8. The sysctl or proc file that you need to modify to bump up that limit, I believe, is the same in RHEL 8 as it is in RHEL 7, but I have not played with it to be sure. Other distributions, if you're on a Cray system, CLE 6 and CLE 7 both support CharlieCloud out of the box. SUSE Linux Enterprise, everything 12 SP2 and newer, including SLES 15, they all support CharlieCloud out of the box with no modifications required. So if you have a current modern Cray system that's running CLE 6 or 7, CharlieCloud will work with no additional effort. For Debian and Ubuntu, any relatively recent incarnation of either of those distributions will fully support CharlieCloud. Any other questions? You're welcome, David. Was there a question from Wayne?
I'm not sure. Oh, he says Martin got it.
Oh, okay, great.
All right. Well, if there are no further questions, we really appreciate your time, Michael, and the presentation. This has been great.
My pleasure. If you're interested in more from me, I recently gave a talk at the Swiss HPC AI Advisory Council conference just a couple weeks ago called Container Mythbusters, where I go and talk about some of the misconceptions about containers and provide corrections and additional information and so forth. You can find it on YouTube under the HPC Advisory Council user. So I encourage you to check it out, and I will provide the link in chat here in just a second for the slides. The link wasn't quite working yet at the beginning of the call. I'm not sure if it's working right now or not, but by the end of the day or first thing tomorrow, it should be working just fine.
you can potentially
All right. Well, we appreciate everybody's time today and joining us on this. Again, we will get this recording posted up as we can, and we'll update the links as Michael provides them to us. But thanks for everybody for coming.